speed, and then also you know, you need to get the correct answer as well as speed. So speed is also important. So depending on the so tomorrow I'll check your performance, and I will basically revise the time limit accordingly. Okay, make sense?
Yes.
Okay, you understand what I'm saying here, right? So I'm going to basically because today is the first time, so I'm giving 75 minutes. So I'll see how everyone will be doing, and then maybe I'll revise the time limit afterwards. Okay. So with that, maybe let's just continue with our class. See here. Do you see the slides? I hope you can see the slides. So this is the additional derivative topics. So basically we're gonna look at exponential and logarithmic functions. So this is a special class of functions, exponential and logarithmic. Okay. So let's try to find the derivative of this e, okay, to the x power. So when we have e to the power of x, so e is the exponential, exponent with the power of x. So we are actually applying the concept of limit. So we are trying to find this answer, okay, the answer to this. So we are applying this definition where we know that. So can you get this? So this is basically we are making use of this definition. Okay, we are making use of this. Now, can you make sure that you understand this? So what is so we are basically looking at this exponent to the power of h. Okay, exponent e to the power of h. Now, what is the value of this when we have limit, when we put limit? Okay, when we are finding the limit when h is approaching 0. What would be the value of e to the power of h? When you make h to be very small, so this whole term will be, any guess? A. We are making h to be very small, right? So what happened to this term when we make h to be very small?
1.
1. Okay, very good answer. Okay, so this is Atik. Atik also. Okay, so you get, so this is 1. You know how did we get 1, right? Because when h approaches 0, when h, so everyone knows that. Any number, when we put the power to be 0, it will give us 1. Right? Any number to the power of 0, it's 1. So when we make this h to be as small as possible, so we are making this to be approaching 1. Okay, so the limit of e to the power of h would equals 1 when h is very small. Now, since this is 1, so 1 minus 1 is 0, isn't it? So 1 minus 1, so here, when you look at the numerator, this is 1. This is, we have 1 minus 1, which is 0, right? 0. Not actually 0, but it will approach 0, right? Because everything is being measured in approaches, right? In limit term. Okay. Let me see. I think there's a few people who want to join in. Just admit them. Okay. So where were we here? Okay. Okay. Okay, so focus at the numerator. So this gonna be very near to 1, right? Very near to 1. So a number which is very near to 1 minus 1, so this, the numerator would approach 0. The numerator would approach 0, while the denominator, when we have h, h itself also approaches 0. So when you have a number that approaches 0 in the numerator, divided by a number that also approaches 0 in the denominator. So this will be very small. This will be a very small number. This will also be a very small number. So a very small number divided by a very small number will approach 1. Okay. When we have a small number, so in the numerator will also approaches 0, because this approaches 1. So a number that approaches 1 minus 1 will approach 0, as well as the h, the denominator, will also approaches 0. So numerator that approach 0 divided by the denominator that approach 0. A small number divided by a small number will give us 1. It will approach 1, the limit. Now, I hope this is clear to everyone, because we're going to basically apply this definition. Okay, we're going to apply this definition. So how do we find the derivative of the exponential to the x power? Okay, so so this is a 1 by 1, just to show you how do we get it. Of course, I mean, once you memorize, once you get used to the formula, the shortcut, it will be easy. You don't have to go through this again. This is just to explain the definition, the concept. How did we get to that answer? How did we get the formula, the shortcut? So the first step, we find, so if we have f, okay, f of x equals e to the power of x, so we're going to do this. So step number 1. So what happens when we change x by a small value? X plus h. So we're going to simply put x plus h here, okay, to the power of the exponent. And by using the formula, okay, for power, since this has the same base, we can multiply them. This is basically equals to this. Okay. So from here, step number 2, we find the difference between the new value and the old value. Okay, after the change and before the change. Okay, before the change. So basically, we are doing this. We take this value minus e to the power of x, right? So we put this back, plug in this value here. So this is the common term, ex. So we collect the common term. So we put ex at the front and we collect. Okay, so we have e to the power of h minus 1 in the parentheses. Okay, now step number 3. Then we need to do this. Divide everything with h. So now we are dividing this with h. We are dividing this with h. And we simply take this out. Okay, put it outside. So we are having this. Okay, focus at this term. Now this term inside this bracket, the term inside this bracket is where we're gonna then, okay, it's similar to here, right? This term. Okay, so this is why step number 4, when we want to find the derivative, we simply analyze this whole term, the value that we found at step 3, and analyze it at the limit. Okay, at the limit. So we have ex. Okay, and then this term. Now, e to the power of x, there is no h here. So from the point of view of h, this is a constant. Right? No h here. So when we make h to be small, this value will remain as it is. It will remain as constant because we are not changing the value of x. We are changing the value of h. So that's why this is simply a constant which we can either you can say it, we can bring it to the front, okay, because this is a constant. So since there is no h here, so this would be a constant. Constant from h point of view. Okay. So we have e to the power of x, which will remain constant as it is, regardless whatever we do to h. And then we have this term. Okay, this term here. So from this term, as what we have applied here, we have defined here. So the limit of this term would equals to 1. And this is why the derivative of exponent to the power of x will give us the exponent itself to the power of x, the same function, the original function in the first place. Okay, so now the shortcut, everyone should be, this is why some of you really love the exponential, how to find the derivative. So the derivative, if f of x equals e to the power of x, then the derivative is e to the power of x itself, okay, based on this. Okay, so caution all this here, I'm going to leave this to you, and take note, this is, we cannot apply this rule, okay, for exponent. Okay, we cannot apply this rule to the exponent. Okay. Now, just to have a review of the natural log. So the inverse, okay, of exponential function is called the logarithmic function. Okay, logarithmic function. So if we have a constant b, okay, so this b would later on would stand for base, which is positive and it doesn't equals to 1. So the logarithmic function y equals to log b of x is equivalent to the exponential form x, okay, equals b to the power of y. So this y would be the power, while this base is here. That's why logarithm. This is the base of the logarithm, so this is the base of the number. The base of the number. Okay. So the domain of the logarithmic function, is from 0 to positive infinity. Okay, from 0 to positive infinity, while the range is from, it can be any real number. Okay, any real number. Okay, while the domain of the exponential function, okay, it can take any real number, but the range, okay, the range must be positive. Only positive real number. Okay, so graphically, okay, the natural log, okay, and the exponential are the inverse. They are exactly, if we have the 45-degree line where y equals to x, okay, along this line. So this is a 45-degree line. So this will act as a mirror. Will act as a mirror. Okay, as you can see here, for a logarithmic function, okay, the domain must be can be any real positive number, but the range can be any real number. Okay, but for an exponential function, okay, the domain can be any real number, but the range has to be positive. Okay, any positive real number. Okay, so there are two mostly used logarithmic function. Okay, common logarithm, which is to the base of 10. Okay, and then we have the natural logarithm with the base of e. Okay, so next would be, how do we find the derivative of natural log of x? So how do we find this? Of course, later on you'll be exposed to the very easy, straightforward shortcut formula. So let's say we want to find it one by one. So from here, so if we have, okay, so let's do the first step. So if we have this, step number 1, we're going to change x by a small value h. Okay, so when we change this, so we have, okay, natural log, okay, x plus h. Right? If we have this, f of x equals natural log of x. So f x plus h would give us natural log of x plus h. Okay, this is what we got here. Step number 2. Now we want to find this. Okay, we want to find the difference between the new term, the new output, and the old output. So we have natural log of x plus h minus natural log of x. And if you remember, okay, the formula for logarithm, for any minus, if we have this, so this, we can simplify this to be x plus h divided by x. Right? This is similar to this. We can rewrite this, okay, in this format. Okay. Now, step number 3. So now just recall that once we have find the, okay, it's written here. So here, so now we are dividing this with h. Okay, we are dividing this with h. Okay, this is a bit, it has, you have to apply a few tricks, okay, few tricks here to find the derivative. So first of all, we're going to separate them. We take h, okay, 1 over h, okay, and then we collect this term. So we can simplify it like this. Now, the trick here is that we need to multiply this by 1. Okay, we need to multiply this by 1. Okay. So this is 1. Okay, this is 1. So we simply multiply the whole term with 1. Okay. And what we're going to do is that we're going to bring this x inside the bracket. Okay, this x, we're going to bring it inside the bracket. Put it inside. So we have this term. Okay, we have this term. Now, this term from the natural log formula for any logarithm, any constant at the front, we can bring it and make it the power. The whole term, we can make it the power of the log term. Okay, the power of the log term. So now we have 1 over x. Okay, 1 over x multiply with the natural log, okay, of 1 plus h over x to the power of x over h. Okay, so now we have h here and we have h here. Okay, we have h here and here. So now next step, number 4, would be to find this. Okay, to find the derivative when we make h to be small. Okay, when we make h to be as small as possible. Okay, so now, is there any h here? There is no h here. Okay, there is no h here. So we can, so this one, regardless of whatever happened to h, x would remain as it is. So this would be a constant. Okay, constant, okay, from h point of view. Okay. Now there is an h here and there is an h here. Okay, so we can, so that's how we bring this to the front. Okay, we bring this to the front. Now, let's try to simplify this. So how do we simplify this? So we simply define, okay, we defined S, okay, S. So if we were to replace, okay, H with S, okay, because X is basically, so focus on H, okay, here, because X is a constant, so regardless whatever we do, I mean, S would remain, X would remain as it is. X is a constant, X is a constant. So all these would be constant from H point of view. So we simply do a simple trick here. We replace this with S. Okay, this is just to approximate. So we want to approximate H with S. Now here H is in the numerator. So we put S, okay, because S, okay, represent this H. And here H is in the denominator. So we put S here. So now we can simply make the analysis, okay, more simple. Okay, more simple. So next step would be, so as S, okay, approaches 0, so this logarithm, logarithm is simply a linear transformation, right? Log is simply a linear transformation. So we can basically take it out, okay, because basically the log of, how do I put this? Limit, okay, log of x similar to log of limit of x. These two would be equal. Okay. Right. Okay. Because this is simply a linear transformation. I mean, there is no s, there is nothing here. Okay, there is nothing here. So whatever the number that we got here, okay, would be the same. I mean, either we find the limit of the logarithm or we find the logarithm of the limit. Okay, both would give us the same answer. Okay, both would give us the same answer. If you don't, my handwriting here is not really good, but let me just try to yes. And if we were to have limit, okay, of any log of, let's say, 2x. Now this would be similar to log of the limit of 2x. Okay, this would be the same. Okay, so this is why we can take the log out and we can simply try to find the limit of this term, the term in the bracket. Okay, the term here in the bracket. So what happened as s goes to 0? Now this seems to be what? Seems to be similar to our definition of E, isn't it? What is E previously? E is 1 plus 1 over n to the power of n, isn't it? This was the definition for E. Now this, by applying this is our exponent. I mean, as s goes to 0, this will then give us, right, this. Okay, so this is why we can simplify this to be the E. And the natural log of an exponent is 1, right? Natural log of E equals 1. And this is why we get, if we have f of x equals natural log of x, so the derivative is simply 1 over x. I mean, the shortcut looks pretty much simple, right? Compared to the step-by-step procedures to get it. But this is just to show you so that you would understand the construction, the mechanism behind how do we get the shortcut. How did we get this shortcut? Okay. Now, so the example, I'm going to leave the examples to you because I think for once you familiarize yourself with the shortcuts to find the derivative for exponent and the natural log, everything would be easy. Okay, everything would be easy. So maybe we'll just do this together. So how do we find y prime? Applying the formula. So this is a constant. So we have Ex. We're going to get Ex itself, right? Plus 5 over x. Okay. Easy, right? So this is why you should familiarize yourself. I mean, use the shortcuts. Because if this question were to come in the exam, I mean, it would be very easy. It would be very easy. So I'm going to leave the other examples to you. Okay, other examples to you. In most applications involving log and exponent, usually the number E is the preferred base, the natural number E. Okay, the natural number E. It's just that in some very rare situations, okay, some rare situations are better handled with a base other than E. Okay, so this is how we change the base. How do we change the base? So I'm gonna again leave this to you because it is pretty much straightforward. You just need to basically be careful as you move from one step to another, okay, because here we are basically applying all the rules with regard to natural log and stuff. Okay. This is how we change a base for exponential. Okay, from b to the power of x, you want to change it to the base of e. Okay, you want to change it to the base of e. Okay. So this will be the summary. Okay, the summary, if we have for exponent, these are the shortcuts. These should be your favorites. So if you have a function of exponent f of x equals ex, so the derivative would be ex itself. And if you have a function f of x equals b to the power of x, then f prime of x would equals to the function itself, but you need to multiply with ln b. How do we get this natural log of b? Yeah, because of this, okay, this one. That's why and if you go through this, it will explain you. Okay, it will explain to you why there is an additional term when we are finding the derivative of an exponential function with a base different than e, okay, with the base b. So don't forget this. Okay. Similarly for log, okay, for log, if you have f of x equals natural log of x, so the derivative is 1 over x, 1 over x. But if we have a function, a log function with the base different than e, because this is basically log of with the base e. If this is with the base b of x, so your derivative, okay, the derivative would have additional term 1 over the natural log of b of that base. Okay, so these are the additional term when we are dealing with functions that are using a base different than e, the natural number. This example, again, I'm going to leave this to you, exponential model as well, okay, because I believe they are pretty much straightforward. And let's move on to the next topic. Okay. So everyone, yeah, still here. Okay. The next topic would be what will it be? It would be some more shortcuts and formulas basically. So these are basically the remaining parts of the derivative, since by now all of you should already have a good understanding of the concept. How do we apply limits? How do we then apply the concept of differentials? So all these would be important, because once you understand all these concepts, all the remaining things would simply be formulas for you to familiarize yourself. You would need to basically do exercise. You need to do more trainings so that you can apply the shortcuts right away. Okay, but applying shortcuts without understanding um, the concept, okay, the definition, the mechanism behind it, I mean, it will be a waste. So that's why I decided to spend lectures, most of the lectures, just to share with you the understanding of these concepts. Okay, by either through definition, through graphical illustration. How do we can find the difference after we change the value? We find the difference, divide by the change itself, and then how this can translate into graphical illustration from a slope of a second line, and then how when we make the change to be smaller and smaller as possible, the slope of the second line becomes approaches the slope of the tangent line. Okay, so once you understand all this concept of how do we measure differences, because derivative is all about measuring differences, measuring changes. When x changes, how will then y change? So all these are measurable. So we are applying all these concepts. And all the remaining, so once you understand the concept, all the other things, so whatever functions that will be given to you, then it will be basically, I mean, easy. Once you understand the concept, you just need to apply the right formula. You just need to apply the right formula. So that's why let's just go through this, the next topic, the next formula basically. So the next formula would be applying some formulas, shortcuts, shortcuts. Just prefer to turn off the mic so that you can focus on the slides. Okay. Slides. Okay, derivative of products and quotients. Okay, derivative of products and quotients. So in the previous discussion, okay, we found that derivative of a sum is the sum of the derivative, okay, and the derivative of a difference is the difference of the derivative. So what is this all about? So this is nothing but, yes, we are saying that if we have f of x equals g of x plus h of x, this is summation, right? Sum. So how do we find f prime of x? We simply differentiate each of them, right? Okay. The derivative of a sum is the sum of the derivative. The derivative of a sum, when we want to find the derivative of this, is simply the sum of the derivative. And similarly for the difference. Okay, the difference. Now we want to check if similar properties hold for multiplication and division. Okay, so we're going to test the theory with an example. So let's say we have these two functions, f of x equals 3x plus 2, and we have g of x equals 2x minus 3. Now we want to basically investigate, determine if the derivative of the product is equal to the product of the derivative. Can we apply the same rule? Can we apply the same rule as we have applied for summation and difference, for plus and minus? So let's see. Now, solution. First, we multiply these two. So if we were to multiply these two, 3x plus 2, okay, multiply with 2x minus 3, we will get, what will we get here? So this would equals to, I think to save time, maybe I'll just, because this should be pretty much straightforward, right? You already know how to multiply this. You should already know how to multiply this. Otherwise, you have to do more questions, more trainings. So we have 6x squared minus 5x minus 6. Now, let's try to find the derivative. Okay, so now the derivative of this would give us 12x minus 5 minus 0, right? Okay, we got this. Now, what about this? Let's try to differentiate the function first. Okay, so this is, so f of x will give us 3, because this is 3x plus 2, and g of x will give us 2. Now, if we were to multiply this, f prime of gx multiply with gx will give us 6, right? These two, if we were to multiply them, 3 multiplied by 2 would give us 6. Well, by doing this, if we were to multiply first and then we find the derivative, we get 12x minus 5. So are these two equal? No, they are not equal. They are not equal. Therefore, we cannot apply the same rule. The derivative of the product is not equal to the product of the derivative. These two are not equal. They are not equal. Okay, they are not equal. Okay. So it is not. Okay, it is not equal. So using the definition of the derivative and the four-step process, basically we can show that the derivative of the product of the two functions is the first times the derivative of the second plus the second term, okay, the second term times the derivative of the first term. What is this? So if we have this, okay, if we have a function which is a product of two functions, f and s. So f represent the first function or the first term, and s represent the second function, okay, in the product. So if the derivative of both these functions exists, then we have to apply this formula. So first, multiply with the first function, multiply with the derivative of the second, plus, okay, plus. Second function, multiply with the derivative of the first function. Okay, so you f remain as it is, differentiate the second, plus now second remain as it is, differentiate the first. Okay. So let's apply this. Okay, let's do one example. So if we have, so these are combination of two functions. So this is our f of x equals 2x squared So what is our f prime of x equals 4x. And our second function is 3x to the power of 4 minus 2. What is the derivative of the second function? 12x. Now, if you want to apply the formula, the earlier formula, so we have, if you remember, f prime of x would then equal to f multiplied with s derivative plus s multiplied with f, isn't it? So this one will give us, okay, so let's just look at the answer here. So what you need to do is you simply rewrite the whole thing back here to x squared multiplied with second derivative is 12x. And then plus second derivative, rewrite the whole the second function, okay, minus 2, multiply everything with the derivative of the first function, 4x. Okay, see, this is f, this is s prime, this is s, this is f prime. So open the bracket, okay, simplify, and you can collect the same term. So this is the answer. Okay, now this is the first method. Okay, this is the first method. Second method, this is the direct attack. So the direct attack is to simply multiply this. Okay, multiply this term. So once we multiply, because it is not that complicated, because the first term is only consists of one, the first function consists of one term only, single term. Okay, so 2x squared multiplied with 3x to the power of 6, so we have to multiply by 3 is 6. X to the power of 2 plus 4 is 6. Okay, and then minus 2 multiplied by 2x squared, so we have 4x squared. Now from this function, we can simply find the derivative. So 636. Okay, x to the power of 5 minus 8 multiplied with x. Okay, so either way, you're going to get the same answer. Okay, the same answer. This is where we apply this formula. This is what I like to use the term as the direct attack. Okay, you expand the function itself. Okay, you multiply it first and then you find the derivative. Okay. Second example, we have two functions. So I mean to do the direct attack might be a bit complicated, but not that complicated. I mean it's still doable. Still doable. Okay, still doable. I'm gonna leave this to you. Okay, this example to you. Leaving this example to you means I'm going to leave this under your care and responsibility. Please make sure you go through it and you understand how to do it. Okay. Lines. Okay. Next, okay, would be the quotient of two functions. Okay, quotient of the two functions. So we have, let's say we have two functions, t, okay, x to the power of 5, and bx equals x squared. Now, let's say, remember how we investigated about the product? Okay, so that should already give you a hint that the derivative of the quotient, okay, is not equal to the quotient of the derivative. These two are not equal. Okay, so tx, the top function, bx, the bottom function, the numerator and the denominator. If we were to divide this function first and only then we find the derivative, it is not equal to the quotient of the derivative. It's not equal when we find the derivative separately and then we divide it. Okay, so let's just investigate this. So let's just try to investigate this. So this is basically, so what is our t prime? Our t prime of x is 5x to the power of 4, and our b prime of x is 2x. 2x. Now let's try to find this. So what is this? So this is basically x to the power of 5 divided by x to the power of 2. So this is equals to x to the power of 5 minus 2, x to the power of 3. Now x to the power of 3, when we find the derivative d of dx, x to the power of 3 will give us 3x square. Okay. What about this method? Now, this is basically when we find the derivative first. We use this method. So this would give us 5x to the power of 4 divided by 2x. So this will give us 5 divided by 2, 5 over 2, multiply with x to the power of 3. Oops. X to the power of 3. Now, these two, they are not equal. Okay, so this is how we found this. They are not equal. Okay, so the derivative of a quotient is not equal to the quotient of the derivative. Okay, now this ratio is what we term as quotient. Quotient. So we need to apply there is a shortcut, but the shortcut is a bit more complicated. It's a bit more complicated. It's not that complicated, but relatively compared to the product rule, the quotient rule is a bit complicated. But once you get used to it, I mean, in life, once you get used to anything, then it will no longer be a challenge. It will no longer be a complicated. Okay. So if we have a function, which is a ratio, okay, in a quotient form like this, then the derivative, okay, of this quotient would be where, first of all, you need to take the okay, if I were to read the technical definition, it will sound very technical. Bottom function multiply with the derivative of the top function minus the top function multiply with the derivative of the bottom function divided by the bottom function to the power of 2. Okay. But you need to, I think, somehow get used to this formula, because it will help you to save time, okay, to find the derivative. Okay, you see, this is the technical the definition. When we put in words, I mean, it will sound so boring. I mean, so perhaps you would rather want to memorize this. Try to visualize this always. Okay. Okay. So this is the quotient rule. If we have numerator, denominator, two differentiable functions, okay, numerator, denominator, or top and bottom. So if both the derivative of both the numerator as well as the denominator exists, then we have the derivative, okay, of this quotient like this, okay, in this form. So using the simplified notation, perhaps this would be much I think look more simple. Okay, would look more simple. Okay. Example. So let's try to do this example together. So we have our t equals x squared. So our t prime would equal 2x. And then we have our b equals 2x minus 1. Our b prime equals 2. Now applying this formula, so f prime of x. So what should we write first? So let's try to do this together. So we have b t prime minus tb divided by b square. Okay. So this will give us, what is our b? What is my b here? 2x minus 1 multiply with t prime. 2x minus tx square multiply with b, don't make a mistake here, b prime, which is 2. And everything divided by 2x minus 1 square. Okay. So now come the fun part, where we simply need to simplify this, expand this. So 2x, 4x square minus 2x minus 4. Sorry, the sometimes you need to be careful when having fun. So this is 2x square divided by, so this would give us, should I leave it? I don't know. Sometimes it's better to leave, but let's say I want to simply expand it and see what I'm going to have. So 4x squared minus 2x. So this one will give me 4 minus 2, 2x squared minus 2x divided by 4x squared minus 4x plus 1. Why did I expand it? Because, you know, if I can simplify this, I mean, I can straightforward see it from the original function here. But if I did not expand it, then I will not see what the product going to be. I mean, this is just my preference. My personal preference, usually when I have this, I tend to expand it so that, you know, if once I have expanded it, I can always compare the numerator with this value and as well as this value, this term and this term. And then I can see if I can simplify them further. Okay. Otherwise, okay, just leave as it is. Okay. Yep. So even the example, leave the answer like this. Okay. In fact, although this one we can simplify this further, right? 2x x minus 1 divided by 2x minus 1 square. Okay. Example 4, additional examples are all under your responsibility, will be under your care, as well as example 5. This is the sales analysis. If we have this sales function, total sales in thousand of games of a video game T, after the game is introduced, is given by this. So you are asked to find the S prime of T. Okay. So we have, this is a quotient. You have your numerator, you have your denominator. Okay, so apply the formula and you should be able to get this. Okay. I'm going to leave this under your care. And next would be, so what is next? Next is the chain rule. The chain rule. So what is sometimes life becomes complicated. The functions given to us may not be direct. Okay, it may consist of composite function. What is composite? Composite, I mean, the function is kind of nested in a, I don't know how to say this. If you you have I don't know, sometimes okay, my mom doesn't really buy Tupperware. No, she doesn't like to buy. Even my wife, yeah, my wife sometimes she buy Tupperware. I mean, if you buy Tupperwares, I'm not sure how to say this. You know Tupperwares, right? It's a famous, I think it's a global brand. I mean, sometimes when you purchase a Tupperware, it is nested. I mean, you have the bigger bowl, inside is a smaller bowl, so it's nested. So sometimes for functions are also like that. You have a simple function which is nested in another function, nested in another function. So they become composite. Okay. I hope you get what I mean. You have sometimes when you purchase a bowl for your mom, a present, although Mother's Day already passed, you want to give present, sometimes you may buy a pot, okay, a cooking pot, okay. So inside that pot, you have a smaller pot, inside you have a smaller pot. It's like boxes, right? Okay, so these are all nested in one another. Okay, so that's what we, what is basically the concept of this composite function. Okay, composite function. So composite function, like this one. So if we have this function, x square plus 4 to the power of 3. Okay, it is actually a combination of what? It is a combination of a quadratic function and a cubic function. We have a quadratic function here. This is our quadratic function. Right? This is our quadratic function. And this is our cubic function. Okay, so the quadratic function is nested inside the cubic function. Okay, so if we were to basically rewrite this, okay, this whole function. So let's say the all the term inside the bracket, we use the notation u. So the function now we can simplify it to u to the power of 3. Okay, u to the power of 3. And what is u? U is simply x squared plus 4. So this is our quadratic function. And this is our cubic function. So this function g of x, which is now we have defined as u is nested inside this function f. Okay, so this is a composite function. Okay, it consists of different functions all together, combined. Okay, keyword here is combination. So we can express y as a function of x. Okay, so this y, actually we can simplify everything, express everything in terms of x. Okay, these are different notations, different ways. Okay, so the function m here, this is the composite of the two functions f and g, because here you can see here the function g is nested inside f. So m is actually a combination of both these two functions together. When they are combined, we have a composite function. When both f and g are combined, we have m of x, a composite function. Okay. Why do we need to know this composite function? Because we can apply the chain rule, which will make our effort to find the derivative easier. Okay, easier. Okay. Now the domain of M, of course, set of all real numbers. Domain, okay, would be the domain of G. Okay, Gx is in the domain of F. Okay. Example. So let's say we have this. Okay. So we have f function of u is e to the power of u and gx is negative 3x. So how do we find f g of x? So what do we need to do now for the first term? Okay, so be careful. So f g of x. So we simply need to take note. This is u, right? So what we need to do is e to the power of e to the power of g of x. Right, we simply replace this u, whatever in the bracket, with g of x. What is g of x? E to the power of negative 3x. Second, g f of x. So this is our first composite function. Second composite function, g is negative 3. Now x, so what do we replace with x? We simply replace it with f of x. Okay, so this would give, f of x. So this one we're going to have negative 3. So this is our e, right? U. Okay. See, we have two composite function. Okay, two composite function. This example, I'm going to leave this to you. Okay. How do we rewrite this? Okay. This is a function, but we can separate them. We can separate them as a composite of two more simple functions. Okay, two more simple functions. Okay, and these two. Okay, so we can combine. Okay, all the terms are under the root. Okay, as u. Okay. So now, how do we apply this? The chain rule. So once we have separated, okay, we have identified a composite function into several components of functions. We can actually apply, okay, all the rules that we have discussed before. because it will be pretty much simple. Okay, it will make our investigation more simple and easier. Okay, it's almost 1 hour, so I don't want to basically take much of the time. So maybe we can leave this the chain rule. Okay, how do we apply the chain rule for our next meeting, inshallah. So I'm gonna stop here, okay, because it's almost 1 hour. So all the best with the test. Okay, you have 2 questions for today. Basically 2 questions every day, except for Friday. Except for Friday, there are 4 questions. Because Friday is near weekend, right? I mean, so that's why I think everyone would really look forward. So, but 4 questions means the questions are not that complicated. So I don't know. I think so. So any issue, any question about the test? You all have the gadgets. I mean, like you can make sure that you can upload your answer. Now for today's, I'll just give you a hint. For today's test, there is a question that require you to draw graph. I think so. Yes. So make sure you have your rulers or your pencils and stuff with you, because either you scan them or you take photos of it and make sure you upload your answer on iTalim. Okay. I really need to get your cooperation to make sure you write your metric number and your section number on every page. So every page, make sure you write your metric number and your section number. Okay. Of course, the coverage of the test, basically it covers since the day that some of you receive some candies from me, right? Our first meeting, so long time ago, when everything was before MCO, okay, until what we discussed last week. What we discussed today, okay, won't be in the test. Won't be in the test, okay? In fact, I think the it will only cover up to marginal analysis in business and economics. So that would be the coverage of the test. Okay. Of course, I won't be able to ask everything. So the questions would be basically scattered. Would be scattered. It's just that some of the derivative question that we have discussed last week, some of the questions, if you remember, but we did, how did we find the derivative? Last week, we did it using the 4 steps, right? Very slow. Step number 1, we find x plus h, and then we find the difference, and then we divide by h, and then we find the limit. Now, perhaps some of you would like to also apply some of the formula, the shortcut that we discussed today and inshallah on Wednesday in the test. Now, that is also acceptable because there will be questions where I ask you to find derivative. But the coverage until last week is only when we discussed the 4 steps, right? The very primitive one by one. But if you want to save time, you can also apply the formula that we have basically discussed today. Okay, because the formula gonna save you time. Okay, because there are always more than one way, right? How to go into Jannah, right? I mean, so how to get the right answer, there are more than one way. So you can, up to you, especially in also in matrix algebra, there are different ways how to find the answers. So as long as the answers are correct, okay? Anything else about the test? No more? Okay, if there's anything, I'm always virtually there in the WhatsApp group. So please let me know. So all the best, and I really pray that you can score. Just that one more thing. Some of the questions I put a note there where I really want you to try to do it on your own. So for those questions, I really would like to request that you try to do those questions on your own. Questions that I did not put any note, basically because it's a take-home exam and stuff, you are free to refer to any materials, you are free to discuss with anyone. But the questions that I put, please do the question on your own. That's really a request from me. Try to do it on your own. Okay. So that's all, and see you inshallah next time. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, sir.